Hello, Greg here, and in this video we're going to talk about scientific reasoning. This is a huge subject, so this is really only going to be a taster. My aim here is to help you understand what scientific reasoning is and to understand some of the rules and the terminology. Many of these terms we'll be familiar with, but maybe haven't thought very deeply about what it all actually means. But this is what we're doing as scientists. We're making logical arguments. We're using our scientific reasoning skills to consider all of the evidence and come to some kind of conclusion. This is the root of critical thinking. And this is what we're fundamentally doing in the results section of our dissertation, is making these arguments and drawing conclusions. So let's just remind ourselves of that whole problem-solving process. In the first instance, we want to clearly define the problem. What do we know? What don't we know? What do we need to know? And think about how we're actually going to go about finding out. What sort of experiments do we need to perform? What sort of analyses and so on in order to answer the question? We need to form early hypotheses based on what we're trying to achieve in our study, and hypotheses in the plural, because as we'll see later, we should be trying to work more than one hypothesis so that we're not biased towards one particular way of thinking. But then, of course, when we have all of these ideas, we'll have too many ideas for the available time, so we need to prioritize. That's a very important part of the process as well, is fitting what we can actually achieve within the available time frame. Once we've made that priority, once we've determined the priorities, then we can plan the analysis. And we've talked about work breakdown structures and schedules and Gantt charts and so on. So again, going through the process of imagining how long these things are going to take and making decisions about what we are and aren't attempting to do during the course of our project. Once all of that front loading, that project planning, that project scheduling has been done, and we've modelled the project schedule to be reasonably sure we can meet the deadline, then we can begin the analysis. So do the analyses, do the measurements and so on, and allow in our schedule sufficient time to actually pull all of the data together, to evaluate all of the data, to make our arguments, to look at all the evidence. And that's the synthesis phase. And very often this is overlooked, and I've seen some reports and dissertations where it more or less says, here's a map I did, and here's another map I did, and then I did another map, and it doesn't actually come to any kind of conclusion. And very often it's because it didn't start with any particular aims and objectives either. So we've got to get this all very well defined and planned out. Then ultimately, at the end of our synthesis, at the end of our process of scientific reasoning and logical argumentation, we come to conclusions, and that's the final deliverable of our study. So it's all about thinking, and it's all about thinking about how we think and understanding how we think, which is a common theme throughout all of these presentations. So let's look at some different ways of thinking. We could consider first principles thinking, and I would strongly advocate first principles thinking. I'm a big fan of understanding the fundamental principles of whatever it is we're studying. So if our subject is focusing on the stable isotope thermometry, then we really need to ensure that we have firmly understood the principles underlying the science of stable isotope thermometry. And we need to put some work into that and write that into our background and our methodology and explain clearly that we understand those principles, because with those principles then we can apply them to all sorts of different scenarios and all sorts of different hypotheses and test out all sorts of different ideas based on the principles. And ultimately then all of that evidence and that argument should lead us to shared true beliefs, We tend not to talk about facts as much as shared true beliefs, because facts have a half-life. They actually are inclined to change with time as we learn more. But the principles as well involve us separating out the ideas from the assumptions. So we'll see later on how we don't want to be basing any of our argumentation on assumptions, on myth or dogma or legend or people suggesting that's how it is. We need evidence. We need shared true beliefs based on actual observations and sound reasoning. So let's look at Socratic questioning. Socrates, of course, a very famous Greek philosopher, didn't write very much down, but very fortunately a lot of other people wrote down what he said. And he had an approach to thinking, to problem solving, to questioning, which has become known as the Socratic questioning technique. So here are the steps in that process. First, clarify your thinking and explain the origins of your thinking. So why exactly do you think that? Challenge the assumptions, as we've said already. If there are assumptions in your argument, then challenge them. Are we sure? What is the evidence? Look for the evidence. And if you cannot find the evidence, then it's just an unjustifiable belief rather than a shared true belief which is supported by the evidence. Also importantly as well, consider alternatives. Just because you have come up with one argument which explains the evidence doesn't mean there might not be another equally valid or strong argument. So try and consider the alternatives. And this is one of the reasons for engaging in discussion and peer review and inviting others to challenge your arguments. And this is what's got lost, really, is an argument is really, in scientific terms, is a very logical process of evaluating the evidence and coming to a conclusion which is supported by the evidence, whereas the word argument has generally been hijacked by the man in the street as something we do when we shout at each other. And that's not what arguments are, and we really need to understand that. Also, consider, once you've come to some conclusion, consider the consequences or the implications. So always be wary of what this will mean. What are the knock-on effects in terms of other aspects of science or society or policy or whatever the relevance might be of your work? And I have seen many studies over the years where people have reported something, they've concluded something with absolutely no consideration as to how that new knowledge might be misused or the implications in terms of other areas of science, because they're just desperate to get the report or the paper published and out the door so they can get on to the next one. And question the original question. So we're always going back to that original question and looking at the origins of our thinking, and that's something we should be doing all the time. So that's Socratic questioning, is questioning everything throughout the whole process. Then you could look at it from the perspective of the 5 whys. We need to constantly be asking the question, why? And why do we say 5 whys? Well, because research has shown that whenever you're asking why, you probably need to ask why 4, 5, 6 times before you actually get back to the root of the issue that you're investigating. So keep asking why. And if you've got kids, don't stop your kids from asking why. That's one of the fundamental ways that we find out about the world. Constantly questioning, constantly asking why. So when we're asking why, we're looking for falsifiable facts, that fact word coming up again, which identify a principle. So if the answer to the question why is because I said so, or that's just how it is, or it's always been that way, then you have just hit an assumption, and you shouldn't base anything on that assumption until you have dug into the assumption and found if there is actually any truth in it and whether any part of that assumption can be justified with evidence. And if it can't, then ignore it. It's not part of the discussion. So just to illustrate that, an example here of ulcers, which were assumed to be caused by stress. And the assumption was that the stomach must be sterile, so there's nothing in the stomach to cause ulcers, so it must be some other cause, it must be stress. Because if there was anything bad in our stomach, then we'd all be dead. And that was the weak reasoning that was used to justify that ulcers must be due to stress. But then somebody challenged that assumption. They actually looked in the stomach and found, in fact, the stomach is full of bacteria, some good, some bad. And one of the bad ones is H. pylori, which after some studies and experimentation we now know plays a pivotal role in the formation of stomach ulcers. So it's always there, but if our biome, if our gut biology gets out of balance for some other reason and H. pylori comes to the fore, then that may well cause ulcers. And that is just an example of how we should not use any of these assumptions. We should also always challenge those assumptions, look for the falsifiable principles upon which we can build a justified true belief based on actual observed evidence. And that leads me to the logic of science summary here from Kevin de la Plante. Kevin is somebody I've been supporting literally on Patreon and working with for several years now, and I've learned a huge amount from him about critical thinking and the logic of science. And he was actually a professor of the philosophy of science and various other things at Iowa State University, I think, until he decided that a lot of philosophers in academia talking to other philosophers about scientific reasoning was not really helping society. So he decided to give it up and start to make training videos to be largely accessible and available for free to everybody, so that the world at large could understand more about science and reasoning and logical argumentation. Because so many of the problems we face in the world, global poverty and global climate change and so on, require all of us to be able to reason and to consider the logical arguments and the evidence and so on. Because in the absence of that, people will just latch on to whoever is shouting the loudest, and they will form their opinions based on assumptions, not on evidence. So I would highly recommend taking a look at Kevin's work. He's got a great library of videos if you want to dig deeper into critical thinking and the logic of science. So go to kevindelaplante.com, the Critical Thinker Academy, and the Argument Ninja website. Some great content there. And this is one of his summary diagrams explaining the logic of science. So the logic is based on a whole series of premises, of statements of some observable phenomena. And all of those statements, the evidence, the premises, are used to make an argument to draw a particular conclusion. And that conclusion is then telling us something about the world beyond our direct observations. So on the basis of that evidence and the argument and the conclusions, we can maybe make some generalizations about the world around us. Or perhaps we can make claims about historical events based on that evidence and the logical relationships and arguments between those various premises. And that's something we do a lot in geosciences in attempting to explain geological history. We could also make causal claims, and that's the root of so many of those arguments, is the evidence telling us how something is causing something else. And we can use that as the basis then of a hypothesis to go out and take further measurements, make further observations in order to attempt to falsify that hypothesis or support it with new evidence. And those are the theoretical models. So out of that argument, we may come up with a series of causal relationships which we build into a theoretical model from which we make predictions. And then we can go out into the world and test those predictions. So that is the logic of science. That's what we do in order to gather scientific knowledge and to learn about the world around us. But these arguments, this process of scientific reasoning, there are many different ways, many different types of reasoning. And I'm just going to touch on two here, which you may have already heard. Certainly, I think you've probably heard of deductive reasoning, and particularly from Sherlock Holmes, where he would always be talking about the science of deduction. But interestingly, in fact, a lot of his arguments are inductive, not deductive. So what is deductive reasoning? Deductive reasoning is based on premises or evidence which are certain. So, for example, sediments that contain in situ marine fossils were almost certainly deposited in a marine environment. So if this sediment contains in situ marine fossils, then we are reasonably certain that it was deposited in a marine environment. Contrast that with an inductive argument, and that might go along the lines of providing strong evidence of the truth of a conclusion. So the sediment has marine fossils. They're not in situ. It has some marine fossils, so that is probable that it was deposited in a marine environment, but not certain. It just has a probability. And I know for sure that this is not necessarily certain, having done some sampling of some terrestrial soils in which I found planktonic forams, which I wasn't expecting. We discovered later that in fact these were blown in on storms. So it just made me think, if I'd found that soil horizon in the geological record with planktonic forams in it, what would I have thought? So that's the difference between deductive and inductive reasoning. Deductive is leading to something which has some certainty, whereas inductive reasoning is leading to something that has some probability. So let's look at the rules and the terminology of those two types of reasoning. So just to reiterate, we start with arguments, a collection of statements, premises which are intended to support or infer a claim or conclusion. And these premises, these statements, have a truth value. They are either true or false. That is a sort of binary characteristic of these statements. They are either true or false. Now, when we start to use that evidence to make an argument, if the conclusion necessarily or certainly follows from those premises, as we've seen already, we call that a deductive argument. So a deductive argument is where the conclusion certainly follows from the premises. If we can make the assumption that all of the premises are true, which they might not be, but if they were all true, does the conclusion follow? Is there a logic to the conclusion? Does it make sense that if all of these premises are true, this is naturally the conclusion we would draw? If we can argue that that is the case, then we might say that this deductive argument is valid. The next step in the process then is to say not if they are all true, but are they all true? And if they are all true, not only is it valid, it is also a sound argument. So these are the rules of the logic of science, of deductive reasoning, and they're very strict rules about how we make these arguments. So I'm sure you've heard these words before, but they do have a very specific meaning in the logic of scientific argumentation. We hear them thrown around all the time, but I'm just raising your awareness here that they do mean something very specific, and we should, as much as possible, try and use them in the way that they have been defined by the philosophers of science. We can follow a similar path through the inductive route. So if the conclusion follows from the premises with some probability, so we haven't got that certainty in our premise, we've only got some probability, then it is an inductive argument. And we can go to the next stage and just think in terms of if all of the premises were true, which they might not be, then does the conclusion follow? And if we can say yes with confidence, if these things are all true, this is the natural conclusion that we can draw in terms of those probabilities, then we can say that inductive argument is a strong argument. So arguments using probabilities, these inductive arguments, are strong, whereas deductive arguments using certainty are valid. Back on our inductive reasoning, if all of the premises are in fact true and the argument is strong, then we will describe this inductive argument as a cogent argument. And again, this is very interesting. This has very specific meaning in the philosophy of science. I actually went and looked these words up in the general dictionaries, and the general dictionaries don't define these words in these ways. But if we are going to be rigorous in our scientific argumentation, this is the way that these words are intended to be used and have some very specific meaning for a logician or a philosopher of science. So just be aware of that and take care in the use of language in your arguments. But we can take it a step further than that. Deductive and inductive reasoning are just two types of reasoning, and there are many. And if you go to the logical reasoning page on Wikipedia, you'll see a whole list of them. But deductive and inductive reasoning are quite common to our day-to-day scientific reasoning. But we can take the inductive reasoning one step further to abductive reasoning. And this abductive reasoning starts with a cogent set of preconditions. And given a true conclusion and a rule, the reasoning attempts to define other possible premises that could support that conclusion. So we started with a set of premises, we went through an inductive argument, and at the end of that we're saying, okay, what other premises could we generate in order to further support that argument? So that's turning it right round in a circle, and this is called abductive reasoning. And this, in fact, is what scientists and detectives pretty much do all the time, because this abductive reasoning enables us to build and develop hypotheses, and these are things that we can go back and test, things that we can go out and either build a new model or collect new data and observations to provide new premises to insert into the argument to strengthen the argument. So the example there, when it rains, the grass gets wet. The grass is wet, therefore it might have rained. Now we can build a hypothesis based on that, and we can go back and collect further evidence of that statement in order to develop that shared true belief. So let's take a look at those hypotheses now. Hypothesis testing. We're forming hypotheses and we want to test them. But what is a hypothesis? Here's a nice definition. A proposed explanation for a phenomenon based on limited evidence which provides the basis for further investigation. So that's that abductive process. We've made an argument, we've drawn a conclusion based on that limited evidence. From that then we've suggested other premises, other observations, other measurements we might make to test that hypothesis. And hypothesis testing, of course, is a core part of the geoscientist's interpretive method. And as we'll see, we shouldn't have one hypothesis. We should be working on several scenarios, several hypotheses, so as I've mentioned before, we don't get bottled in and biased to one way of thinking. So that method of multiple working hypotheses was first published, I think, by Chamberlain in 1897. And he was one of the original researchers who advocated that we shouldn't focus our research efforts on one hypothesis because we may become biased towards that hypothesis. Got the wrong teeth in this morning, I think. And we need to consider all possibilities. So we should always keep our ideas broad and think of many different possible explanations of our current evidence, because that enables us then to avoid biases such as confirmation bias or availability bias, or maybe overconfidence in a particular explanation, or groupthink, where a whole group of us are all sold on this idea and we're relentlessly pursuing this particular hypothesis, and we're only paying attention to evidence which fits the hypothesis. And this whole groupthink leads on to paradigms and paradigm shifts. And elsewhere I've dealt with this issue as well. And if you're interested in paradigms and paradigm shifts, I recommend you watch the video series The Men of Rock by Ian Stewart, which looks at the history of geoscience through Hutton and Lapworth and various others, and see how they were biased and they were exposed to groupthink, and they were on bandwagons and they were following certain paradigms, and we had to have substantial paradigm shifts before we could improve our thinking and move on with our understanding of the geological world. So don't put all of your eggs in one hypothesis. Keep an open mind. Think of all of those possibilities, those different options. So then we can think about hypothesis testing. How do we actually do that? Well, we can go about this in a couple of ways. And one way is to build models. So there's an example from Gilbert, 1886, who describes the variable elevation of the Lake Bonneville paleo shoreline. So this is a paleo lake, which is the sort of precursor of Salt Lake in Utah. And from the evidence in the landscape, you can see that this paleo lake shoreline has changed many times throughout its geological history. So what Gilbert did is he put forward 3 hypotheses, so he's testing multiple hypotheses, and the way he tested them was to build a whole succession of models. So based on the premises and the arguments for each hypothesis, he constructed a model to test those premises, those causal relationships. It's a theoretical model from which he was able to make predictions. Now, going through that process, only one of his models stood the test and survived the falsification process. So on that basis, then, he concluded that this third model was the most likely explanation for the shifts in paleo shoreline. But he then does go on to say that you should continue to test and try and falsify that model. That's the outcome of that model, the apparent confirmation of that hypothesis. You should test by collecting further evidence, attempting to falsify the model, and if you continue to fail to falsify it, then that conclusion will stand until such time as somebody finds the evidence to falsify it and comes up with a different hypothesis. And this essentially remains one of our fundamental methods of hypothesis testing in geoscience. We could also take the approach of the data-led approach. So Cleland has argued that it's typically difficult to falsify geoscience hypotheses because the events are too complicated, the time frames are too long, and experimental tests are too difficult, particularly tests, obviously, of things which have happened in the geological past. We can't go back and test in real time. We're always basing our observations on some kind of smoking gun. We have to look for some evidence from the rock record which is an outcome of our suggested system or conclusion. So an example of this is the dinosaur extinction. So geoscientists looking at that horizon, trying to understand what might have happened at that horizon, doing detailed analyses, discover that at the stratigraphic horizon where dinosaurs largely disappear, there's an iridium anomaly. Now, iridium is present on Earth, but in very low quantities, but it is very, very common in meteorites. So the hypothesis then was formed that there might be a meteorite impact at that time. So then the challenge was on to go and find where this meteorite impacted and any other evidence of that meteorite impact. So I think then, having established that that might be a possibility and forming that hypothesis, a lot of other evidence was found until eventually, having focused in on the Gulf of Mexico or Central America as the most likely impact area, then the explorers, and in particular Gravenmag and seismic people, were able to discover the meteorite impact crater, which we think caused that extinction. So in this case, rather than doing lab experiments or building models, the hypothesis was tested by going out and looking for evidence in the field, looking for those smoking guns. And this is another approach, and this links into indirect hypothesis testing. So this might be where we're combining both models and data. So based on our initial observations, we've built a model which is a sequence stratigraphic model. So this schematic model is showing 4 parasequences. The green represents continental sediments, the yellow marginal marine sediments, and the grey offshore marine sediments. And what we're seeing is a series of progradation and flooding cycles. Each one of these 4 layers is a parasequence. And in this particular stacking pattern, this is what we call aggradational. They are stacked on top of each other. The shoreline in general was stationary, it was oscillating, but its overall average position was in the same place. So we get a stack of these parasequences. And if we were to drill a borehole, we might see shale, sand, shale, sand, shale, sand. And from our model and the data in that borehole, we can conclude that it is an aggradational stacking pattern. From that model, based on the causal relationships and that theoretical model, we can then predict that if we go further west, we might find a continuous sequence of marine sand. And we can test that with field data by drilling another well and looking at the cores and the logs. So this is indirect hypothesis testing. It's using a combination of predictive models and then field data testing to confirm or refute the predictions from the hypothesis and from the model. So that's something we do all the time as well. So a cycle of field data, hypothetical model, making predictions, testing with field data. While we're looking at terminology, I'd also like to take a quick look at a priori and a posteriori. And I've always wondered how to pronounce them, so I actually put them into Google Translate and switched it to Latin and got Google to play it back. So if I was doing this in Latin, it would be a priori and a posteriori. Now we see these things written in journals, and for a long time I would read it and think, okay, somebody else trying to impress me with their Latin. But they do have a specific meaning, and I think it's important that we are aware what that meaning is. So quite literally, a priori means from the earlier, compared to a posteriori, which means from the later. So what does that actually mean? So from the earlier, we mean something, some premise, some piece of knowledge which is independent of experience. It's not something that we have to observe or measure. It's something like mathematics or deductions from pure reason. So these are conclusions that we can draw based on mathematical experimentation or based on a scientific deduction. We don't actually have to make an observation. We don't have to have an experience of the thing in order to come to the conclusion. So that is something we can know before we go out and observe the world. And that is particularly important in Bayesian statistics. I'm not covering that here, but Bayesian statistics is a method of statistic prediction which is based on first establishing priors. So making a statement of what we believed we know before the conditions change. And those are called priors in Bayesian statistics, a very powerful predictive method. Compare that to a posteriori, and these are this is knowledge or justification of an argument which can only be known after the event. So we have to have the experience, we have to have the observation. It's a conclusion that can only be drawn from making the measurement. It's not something we can conclude based purely on deductive reasoning. So when you see those words, a priori is something we can justify before based on reasoning, or a posteriori is something which we will only know after the observation, the experience, the measurement. It's empirical, basically. So that's a little indication of a priori and a posteriori. Let's take a quick look as well at circular reasoning. This is something you'll hear people talk about. And circular reasoning, to a certain extent, is frowned upon in the philosophy of science world. It's not considered to be a good way to reason. However, it is something which we use quite a lot in geoscience. Now, this is an illustration here from Pete Horton, a very clear thinking guy who I had the good fortune to share an office with many years ago. But he has a great way of constructing really great, clear, logical diagrams that tell a story and make it clear to us what's going on. And this is one of his diagrams from deep water depositional systems, showing how certain petrographical characteristics can be tied to the structures at the bed scale, and how those beds can be put together into a stack with a certain set of relationships he calls a bed stack, and how those make up a depositional element, and you can stack the elements together, and the elements make up a system, and you can stack the systems together. Lovely logic, lovely explanation of all the different scales of observation. But what I'm using it for here is that if you make an observation of something at a certain scale, then you can maybe predict that something exists at a larger scale. And if the thing at the larger scale is observed, then we should also be seeing another thing at the smaller scale. So we keep having these sort of circular reasoning arguments whereby we predict something should be here, and if this is here, then this should also be here. And that's something we do all the time. We keep going back and forth between the scales using a sort of circular reasoning to give us ideas about what else we should be looking for in order to make new observations and provide new premises to support our arguments. So that's the sort of concept of circular reasoning. Be aware of it, be aware that that's what you're doing, and just be prepared that somebody might challenge you that that is a circular argument. But in geoscience, it does seem to be acceptable if you can justify it logically. We've also talked a lot about analogues, and analogues are a very important part of our problem solving and thinking process, and we should use analogues. but we should also use them thoughtfully. Remember the discussion about narrative fallacies, and there are numerous examples littered throughout geoscience where analogues have been advocated, and based on that analogue, explorers and so on, have followed relentlessly that one idea, desperately trying to find something which is equivalent to the analogue. And in doing so, in the case of that porphyry copper example we spoke about before, have excluded all sorts of other possibilities. So yes, analogues are good, and analogues are a very valuable way of considering all the possibilities and giving us ideas, but don't jump onto one analogue and pursue it to the exclusion of all of those other possibilities. Again, that is just going to draw us into confirmation bias, availability bias, groupthink, overconfidence, and so on and so forth. And if you're interested in that delta example, I have compiled all of the world's deltas in Orton and Redding's classification of deltas, and I've stuck them all on a Google map, and you can find them on the geolumina.org website. And in the resources area, there's also a Google map where you can contribute your own Google Earth observations. So please take a look at that and share some of the things you've found in Google Earth. Okay, so just to finish off, hopefully that's given you a bit of a whistle-stop tour of scientific reasoning. It was really just to look at the terminology, to look at the rules, to become aware that there are quite strict rules and terms applied to the logic of science and to scientific reasoning, and we should be aware of those and try as best we can to use the right terminology in the right context, and to construct our arguments using that deductive logic or that inductive logic, and to understand whether we are looking at valid or strong or sound or cogent arguments, and also to understand how inductive can lead to abductive, which leads to our hypotheses, and then the different ways that we're testing our hypotheses through modelling or through the acquisition of more field data looking for the smoking gun. So it's really just, as I say, a quick tour, and you should think about it and build on it and do some further reading, look up some of those references in there, and just consolidate your understanding of the logic of science. Because this is the foundation of critical thinking. And that's what we're attempting to demonstrate in our thesis, in our dissertation, in our technical report. We're attempting to demonstrate to the reader that we have gathered the evidence, we have formed the argument, we have drawn a justifiable conclusion, we have justified true beliefs, which we can justifiably believe and use as the basis for further study, further analysis, and so on. Be mindful as well of all those cognitive biases which I keep throwing up. Those are the things which are going to trip us up and lead us down particular alleyways to the exclusion of other possibilities. And we really have to find ways to avoid those biases, both by changing our own behaviour, but by also following the systems that are put in place by your organisation to ensure that we don't fall into these bias traps in our reasoning. And do think about how you think about how you know, and think about how you problem solve, and always bear these things in mind when you're constructing your dissertation, your report, and the arguments in your results section. And ultimately, of course, this is all underpinned by that fundamental understanding of the processes of scientific reasoning and logical argumentation. So hopefully that's helped you to understand some aspects of the logic of science. Many of you will have come across these things already, and you may even have been taught some of these things. But what is interesting, I found after discussion with Kevin, that in fact, although we do a Bachelor of Science degree, and many of us may have PhDs, which means we are doctors of philosophy. which philosophistry basically means a love of the logic of science. And yet so many with a BSc, an MSc and a PhD don't really have the first idea about the logic of science and logical argumentation and scientific reasoning. They may well be doing something that looks like it, but that's really out of habit rather than from understanding. And I put myself in there as well. It's not until sort of recent years that I started really digging into this to find out what it was all about, and realised and understood so much better why I was doing what I was doing, which of course enables me then to do it better. And that's what I think and I hope we're all striving to do. Okay, that was a long one. Sorry about that. I didn't want to break that up. I wanted to keep the flow of that story going. I hope you got something from that. I hope you enjoyed that. And as always, if you have any comments, then please go into the forums and ask questions and see what other people are saying. And I look forward to seeing you again in the next presentation. Bye for now.